Hello friends, welcome to CEC Gurukul live lectures. Dear friends, today in this session we are going to continue further in our series on mathematical methods for economics. Dear friends, this is 7th lecture in this series and today we are going to talk on linear functions. We are going to discuss in detail what linear functions are. Friends, for the discussion on the topic, we have with us in our studios Dr. Neeti Bhutani. Dr. Neeti Bhutani is Assistant Professor in Department of Economics, Hindu College, University of Delhi. Dr. Bhutani is a prolific professor and through her we always get in-depth knowledge on various topics. Friends, if you wish to ask questions from Dr. Neeti Bhutani on today's topic, feel free to talk to us to our toll-free number. Our number is 1800110430. I repeat, our number is 1800110430. Now I would like to welcome our guest Dr. Neeti Bhutani once again. Hello ma'am, welcome to the lecture.
Hello Geetika, thank you so much. Hi everyone, we're back again to talk some more about mathematical tools for economics. This is lecture 7 and the main topic for today's lecture is linear functions, or simply speaking, the straight line. As always, we will first cover the theoretical concepts of linear functions, and then we'll look at some examples to see how the concept of the straight line can be used in economics. But I have two pending tasks to finish before I start with my discussion on linear functions. Firstly, I'm going to talk about, I have to discuss the distance formula and the section formula. These are two results from coordinate geometry, which I had started talking about in my previous lecture. So we'll talk about these two formulas. And secondly, from today, we are also going to start drawing graphs. In fact, when I was a student, I had this professor who would say that the best way to understand mathematics is to draw a graph. And the way I see things, the way this course is structured, this course is designed in a way so as to teach you just those tools which are needed to be able to draw a graph. So wherever possible, try and draw a graph for your analysis, because a graph gives you that visual with which you can understand things in a better way. But we'll get to graphs in a bit. Let us first talk about distance functions, the distance formula and the section formula from coordinate geometry. So let us suppose we have two fixed points, P and Q. The point P is represented by the coordinates. Please see where my cursor is pointing. Please look at the picture on slide 2. The point P is represented by the coordinates x1, y1, and the point Q is represented by the coordinates x2, y2. Let us suppose the distance between the point P and the point Q is given by, is represented as d, and it is for this d that we want to find an expression, a mathematical expression. But before we find a mathematical expression for d, let me talk a little bit about this point R, because this point R, where my cursor is pointing right now, is going to be crucial for getting the result that we want. Now, how do we get this point R? What I've done here is I've dropped a perpendicular from the point Q, which is shown in this as this dashed line, and then I've also drawn this horizontal line from the point P, and these two dashed lines are then meeting at R. What is crucial here is that we should know what the coordinates of R are. Now, the x coordinate of R will be the same as that of Q, because both R and Q are the same distance from the y-axis. Also, so let me just back up. So the x coordinate of R would be x2. Now, if you look at the y coordinate of R, note here that R and P are at the same height. So the y coordinate of R would be the same as the y coordinate for P. Therefore, the y coordinate for R will be y1. That is, the coordinates for R are x2, y1. Also note that what we have here is a right angle triangle, PRQ, and therefore we can use the Pythagoras theorem, which states that PQ square, the square of the hypotenuse, is equal to the sum of the squares of the other two sides, which is PR square plus RQ square. Now, PQ square is nothing but D square on the left hand side. If you want to get an expression for PR, PR is nothing but the horizontal distance between P and R. So that is going to be x2 minus x1, which is what I'm showing here where my cursor is pointing. So PR square would be x2 minus x1 the whole square. Now similarly, RQ is a vertical distance between the points R and Q, and therefore this distance would be y2 minus y1. The x coordinate is the same, so RQ is going to be y2 minus y1, and therefore RQ square is going to be y2 minus y1 the whole square. So this gives us an expression for the distance between 2 points P and Q, x1 comma y1 and x2 comma y2 on a plane, which is that D is equal to the square root of x2 minus x1 the whole square plus y2 minus y1 the whole square, and this is called the distance formula. Now note here that x2 minus x1 the whole square is the same thing as x1 minus x2 the whole square. Also, y2 minus y1 the whole square is the same as y1 minus y2 the whole square. So the point here is, it doesn't matter which point we call P and which point we call Q. We could alternatively write this distance formula as D is equal to square root of x1 minus x2 the whole square plus y1 minus y2 the whole square. And this way we can take either coordinate first. The second result that I want to talk about from coordinate geometry is what is popularly called the section formula. Now, the idea here is that let us suppose we have a point S. This point S divides the line segment PQ. Please look at this picture on slide 4. The point S divides the line segment PQ in the ratio lowercase p to lowercase q, which is to say that if we take the ratio of the segment PS to SQ, then PS divided by SQ is going to be equal to lowercase p divided by lowercase q. Now the objective here is to get an expression for S. S here is our moving point. It is given by the coordinates s comma y, and we want to find an expression for the x coordinate of S and also the y coordinate for S. So let's see how this can be done. What I'm going to do first is I'm going to first look at the mathematical expression for the x coordinate of the point S. For this, I have dropped a perpendicular from the point S onto PR, okay, and this point T here is now represented as x comma y1. The x coordinate of T will be the same as S, and because T and P are at the same height, the y coordinate of T will be the same as the y coordinate of P. So therefore, we have y1 as the y coordinate of T, and T is given by the point x comma y1. Okay, so if you notice here, we have this situation, a geometric, we have this geometry such that if we see ST, the segment ST is parallel to QR, and we know this result that whenever ST is going to be parallel to QR, it is going to divide the sides PQ and PR of the triangle PQR in the same proportion, which is to say that PS by SQ, please see where my cursor is pointing, has to be equal to PT by TR, because ST is dividing both sides PQ and PR in the same proportion. Alternatively, you could also use the result from similar triangles, because here we have the case that triangle PST is similar to triangle PQR. So therefore, PT by TR is equal to PS by SQ, and that is equal to P by Q. Now let us see what PT and TR are. PT is the horizontal distance between P and T, which is x minus x1, and TR is the horizontal distance between R and T, which is x2 minus x. So therefore, we have that x minus x1 divided by x2 minus x has to be equal to p divided by q. Let us now solve this equation for x. So if I cross multiply, I get q times x minus x1 is equal to p times x2 minus x. And if we open the brackets now, on the left hand side, I'll have qx minus qx1 is equal to p times x2 minus p times x. So because we have to get an expression for x, the x coordinate of the point S, we are going to collect the x terms, and therefore we can take the term p times x to the left hand side to get p plus q times x, because we also have qx on the left hand side, and we can take the term qx1 to the right hand side to get p times x2 plus q times x1. So this in turn implies that x is equal to p times x2 plus q times x1 divided by p plus q. And this then is the result for x. Similarly, we can get the result for y, which is that the y coordinate is equal to p times y2 plus q times y1 divided by p plus q. And this is something I'm leaving for you as an exercise. The y coordinate, you can derive the expression for the y coordinate, you can derive on your own by dropping a perpendicular from S to QR now. Instead of dropping it on PR, so instead of this ST being parallel to QR, you will have a segment ST, if I call that point T, where the perpendicular hits QR, that ST will now be parallel to PR, and then you can just follow the same procedure that I have followed for getting the result for x. And this then gives us what is known as the section formula, where the coordinates of a point S that divides the line segment PQ in the ratio P is to Q are given by these expressions highlighted in this orange-yellow color. Now this section formula actually has an interesting implication. Let us suppose we put p, this lowercase p, equal to half, and we also put q equal to half in this formula. Then that is to say that the point S is now the midpoint of the line segment joining P and Q. So if S is a midpoint, then the coordinates of S are now given by x comma y is equal to x1 plus x2 divided by 2, comma y1 plus y2 divided by 2. Right. So this is as far as coordinate geometry was concerned. Let us now talk a little bit about graphs of equations in two variables. Let us suppose we have an equation in two variables, x and y. And let us suppose we have a pair of numbers a comma b, such that when I substitute x equal to a and y equal to b in the equation, that equation is satisfied by this pair of numbers a comma b, or the ordered pair a comma b. So this ordered pair a comma b that satisfies the equation is known as the solution of the equation, and the set of all possible solutions is known as the solution set of our equation. The graph of an equation in two variables is nothing but a plot of the solution set. It is a plot of all the possible solutions of all the possible ordered pairs that comprise the solution set of the equation. To see an example, let us take the case of a straight line. We know that y is equal to, you're familiar with this kind of an equation, which you know represents a straight line from school math. So here we have y is equal to 2x plus 4. And if we look at some points which satisfy this equation, so for example, we could put x equal to minus 3, and that would then, suppose I plug x equal to minus 3, that's going to give me minus 6, and then I have to add a 4, so that will give me minus 6 plus 4, so that y is equal to minus 2. Similarly, if I put x equal to 0, I'm going to get y equal to 4. So here you can see some of the points that I've taken which are solutions for this equation. And these points are illustrated in this graph below. all I have done is I've connected all these points through a straight line. Now, obviously, until and unless you know that this is the equation of a straight line, you wouldn't know what's happening in between the points. So clearly, we need more information than just having a couple of points before we draw a graph. But the idea here is that if we were to have all these points, then all the points on the graph, all the solution set, then that comprises the graph of the equation. And in any case, you would know that to draw a straight line, the minimum information that you need is either 2 points, or if you have information on 1 point, you would need to know the slope along with that to be able to draw the straight line. Let us look at the next example. Now, the next example you would recognize as a circle, I'm sure. So this is our equation here is x squared plus y squared is equal to 4. Now here, if we look at possible solutions for this equation, I could, for example, substitute x equal to minus 2 to get y equal to 0. So here what we can do is we can write y as plus minus square root of 4 minus x square, and then get the corresponding values for y. And these are some of the points which I have plotted for you on this graph. And again, the question is, how do we know what's happening in between the points unless we know that this equation is a circle? That's a good point. Yes, we need to have more information before we can start joining points in a certain way. And that is why we'll be very soon, we'll start talking about differential calculus, and we'll see that a lot of our graphs will be easy to handle with knowledge of differential calculus. But since we're talking of a circle here, let me, as an aside, just quickly talk about the circle in terms of coordinate geometry. A circle is basically the locus of a point, locus as in it is a curve or a set of points that moves at a constant distance from a fixed point. The fixed point is called the center of the circle. So look here, please look at here at this graph on slide 10. The fixed point here is the center of the circle. It's called the center of the circle, and it's represented by the coordinates a comma b. And the curve is such, the circle is such that the curve is at a constant distance, which is called the radius. The curve is at a constant distance from this center. So suppose I take a moving point x comma y, which could be any point on this circle. This point x comma y has to be at a constant distance r, which represents the radius. This point has to be at a constant distance r from the center described by a comma b. Now look here, if we have these 2 points x comma y, which is our moving point, and the center a comma b, and we know that the distance between them is r, then clearly by the distance formula we have that x minus a the whole square plus y minus b the whole square is equal to r square. And this then is our equation of a circle. So in the example that we had, done on the previous slide, here we have a situation where we have x square plus y square is equal to 4. So clearly our r, the radius is 2, and the circle is going to be centered at the origin because we didn't have any a or b terms in that example. So this is as far as the basics of a circle are concerned. We'll be doing some interesting problems on the circle very soon, but I'll try and finish the discussion on functions before I come to the circle. We've all discussed this last time, that the circle is not a function, because if you draw a vertical line through this circle at any point, then the vertical line, the circle will fail the vertical line test of a function, because the vertical line cuts the circle more than once. So we leave the discussion of the circle at this point, but let's start with our discussion on linear functions. A linear function is graphically represented by a straight line which extends indefinitely in both directions. The question now is, why should we study linear functions, or how are they useful in the field of economics or any professional field? So the answer here is that linear functions are they are a simple tool, and they provide a simple tool, and they are easy to handle mathematically. Also, in economics, very often we come across some non-linear relationships. So, for example, if you take a look at this visual here that I have for you on slide 11, here you have this curve which could probably represent price. So, you could think of the y-axis representing price and the x-axis representing time. So, we see that the price might actually follow this curvy curve here. If you see the one in blue, let's suppose this represents the actual movement of price. Now, actually, to follow this curvy curve throughout might be a little complicated. You might even have more complex graphs. But what we can do is we can fit this linear trend. So, if you look at this orange line, this is it's a straight line which we can fit to sort of average out the movements, and this then provides a linear approximation to non-linear relationships. So this is something, this is an idea, a concept which is used very often in economics, and especially when you do empirical work in economics. Right, so let us talk a little bit about the conceptual notion of a linear function. So a linear function between two variables x and y is given by f of x equal to ax plus b, where both a and b are constants. Now, strictly speaking, the function f of x equal to ax plus b, where b is not equal to 0, is referred to as an affine function. Please note where my cursor is pointing. This expression, this mathematical expression where b is not equal to 0, as far as mathematicians are concerned, this is called an affine function. Mathematicians reserve the term linear function for a function which is of the form f of x equal to a times x, where b is equal to 0. So, in the true sense of the word, a linear function is given by f of x equal to a times x. But as far as economists are concerned, so suppose an economist says that he is using a linear function, he is in all likelihood talking about the function ax plus b. So, economists use linear functions for functions of the type ax plus b. Also, because we'll be talking about graphs, we are now bringing in graphs everywhere. So, let us get a sense of what we mean by a graph of a function. So, till now we were talking about the graph of an equation, but what do we mean by the graph of a function? So, a graph of a function is simply a plot of all points x comma f of x, where now x belongs to the domain of f. This is where the change happens as against the case where we have a graph of an equation. Here, when we talk about the graph of a function, it is important that x belong to the domain of the function. Also, whenever we talk of drawing a graph, an important aspect of drawing a graph is the slope. And let us talk a little bit about the slope of a linear function. Now, slope in a generic sense, the slope or the gradient represents steepness. It is a measure of how steep something is. So, in the context of a straight line, the slope or the gradient would tell us how quickly the line is increasing or decreasing. Now, to get a visual sense of things, take a look at this picture here. So, here I have this red line, a green line, and you can think of this blue x-axis as your flat road, and you can also think of this these red and green lines as some two kinds of mountains that you might climb for a trek. Now, clearly, if you think in terms of steepness, you are definitely going to find it more difficult to climb this red mountain than you would climbing this green mountain. So here we intuitively, just to give you a sense of steepness, so here we would say this red line is steeper than the green line, and then this blue line would just be like a flat road and you're walking on this road, and this would have zero slope. So slope, basically, when we talk of slope or the gradient, we're referring to steepness. Now, let us also get a sense of where these kinds of words are used in everyday usage. So, for example, if we are talking of, let's say, a railway track or a ski slope, sometimes you might find written somewhere that, let's say, for example, a railway track has a gradient of 1 in 10. 1 in 10 is written as the gradient. Now, what does this mean? The way you are going to read it is, it means that the railway track rises 1 meter vertically for every 10 meters horizontally. So, we are basically looking at the vertical rise for the horizontal rise, over the horizontal rise. And mathematically, when we talk of the slope, this is represented by delta y, change in y upon change in x, or the change in the vertical distance divided by the change in the horizontal distance, which is also referred to by people as rise over run. And I'll just talk about this a little bit more in a bit, what we mean by rise over run. In particular, the slope measures the change in the value of the function when x increases by 1 unit. So, let us suppose the change in x is when x changes by 1 unit. We have in the denominator, the change in x would be x plus 1 minus x, and in the numerator we want to look at the change in the value of the function when x increases by 1 unit. So, that change in the value of the function would be f of x plus 1 minus f of x. Now, if you notice, the denominator is nothing but 1 because the x's cancel out. So, the slope is given by f of x plus 1 minus f of x. Let us substitute for these values from this function. Now, f of x plus 1 would be a times x plus 1 plus b, and f of x is what we have to subtract out from here. So, f of x that would be minus ax minus b, and you can, once you open up the brackets, you see that the b terms get cancelled as well as the a times x terms, and you are left with a, which is the mathematical representation of the slope of a linear function. Right. So, let us get a visual sense of what this slope stands for and what happens when a is positive or negative. Now, here we have a panel of 3 graphs. If you look at the first graph is 1, and by the way, let me back up. You can see on all the 3 graphs I have shown this b, which represents the intercept in each case. The intercept is the value of y when x is equal to 0. So, having said that, let's now talk about the slope, or let's first talk about the slant. So, if you look at the first graph, this is the graph. This is a graph that slants upwards from left to right, and here we have that as x increases, y also increases. So, if you look at the mathematical expression for the slope, which was given by f of x plus 1 minus f of x, because every time x increases, the value of the function will be higher. Therefore, f of x plus 1 minus f of x is in this case going to be positive, or a is going to be positive. So, if a is positive, we have a line that slants upwards, that slopes upwards from left to right. Similarly, if a is negative, we have a line, because now what will happen is if x increases, y is going to decrease. So, if a is negative, then the line will slope downwards. If a is 0, then we have simply, if I put, you can see here, if I put a equal to 0 in this equation, then our equation will boil down to y is equal to b. So, then we just get this horizontal line, and therefore, we have that if a is equal to 0, if the slope is 0, we get this horizontal line, or vice versa, because a horizontal line will have a 0 slope. Then final case is the case where you have a vertical line. Now, for a vertical line, the slope is not going to be defined, because mathematically the slope is given by delta y upon delta x, and here we see that because there is no change in the x value, so we are in this situation where we are dividing by 0, and we know that division by 0 is not defined. So, the slope of a vertical line is not defined. Now, this slide shows you an alternative representation of the slope, which is in terms of this angle theta, which the line makes with the positive direction of the x-axis. So if we define theta as the angle that the line makes with the positive direction of the x-axis, then if theta is acute, you can see here, this angle here is acute, then in that case the line will slope upwards. But if theta is obtuse, then the line is going to slope downwards. Right, so let us now get into the actual calculation of the slope. So let us suppose we have a line that passes through the points P and Q, where P is given by represented by the coordinates x1, y1, and Q is represented by x2, y2, and as before, R is given by the point x2, y1. Then the slope of this line will be given by QR upon PR. This is the concept of rise over run, because the change in the vertical direction would be QR. When you move from P to Q, the change in the vertical distance is QR, so that is the rise. And the run, which is like running on a flat road, the run is PR. So QR upon PR represents the slope, and that is given by y2 minus y1, because QR has the same x coordinate, but the y coordinates are different. So QR is given by y2 minus y1, and the denominator PR is x2 minus x1, because P and R are at the same height, but the horizontal difference between them will be x2 minus x1. And clearly, because division by 0 is not allowed, we have that x1 should not be equal to x2. Okay, now very often one is interested in knowing how the slopes of different lines vary, or how different lines compare in terms of slope. So suppose I give you three lines, L1, L2 and L3. Please take a look at slide 19. Then intuitively, I think you would all say that line L1 is the steepest, and that indeed is true. So let us look at the mathematics quickly. The slope of line L1, let's represent it as A1. That is going to be given as AM upon OM. The rise is AM, and the run is OM. So the change in vertical, change in Y is AM divided by OM. Similarly, the slope of line L2 is BM upon OM, and the slope of line L3 is CM upon OM. And you can clearly see here that AM upon OM is greater than BM upon OM is greater than CM upon OM, which is to say that the slope of line 1 is greater than the slope of line 2 is greater than the slope of line 3. So we have this result that when we have a line that is upward sloping, the larger the value of A, the steeper is the line. The larger is the value of the slope, the steeper is the line, and that is also consistent with what we intuitively felt. But things are a little different for downward sloping lines. So if I give you three downward sloping lines, please look at slide 20, L1, L2 and L3. Now if I ask you which line is the steepest, now intuitively you would say L1 is the steepest, because suppose you were rolling down any of these three lines, let's think of these as hills or something, and clearly you would roll down the fastest on line L1. So intuitively you would say L1 is the steepest, but there is a catch to the story here. Now let's just look at the slopes individually. The slope of line L1 is minus OM upon OA, because now this is a line that passes through MA, so you're starting from M coming to A. The rise is the negative of the vertical distance, so it will be minus OM upon OA. And similarly, the slope of line L2 will be minus of the change in vertical distance, which is OM divided by OB. And similarly, the slope of L3 is going to be minus of OM upon OC. Now, OM upon OA is greater than OM upon OB is greater than OM upon OC, because OA is less than OB is less than OC. However, because our slopes now have a negative sign, each expression for the slope has a negative sign in front, we have that minus of OM upon OA is less than minus of OM upon OB is less than minus of OM upon OC. which is to say that actually the slope in mathematical terms for the first line is the least. It is A1 is less than A2 is less than A3. So why are we getting a different result? Mathematically, this line L1 has the lowest slope. But the point here is that if we ignore the negative sign and we look at the absolute value of the slopes, then we have that OM upon OA, which is the absolute value of the slope of line of the first line. OM upon OA is going to be greater than OM upon OB is greater than OM upon OC. So if we interpret this absolute value of the slope to represent the steepness of the line, then in that sense our result would be absolutely right, that this first line is the steepest because it has the largest value of the slope in an absolute value sense. So our result here is that for a downward sloping line, the larger the absolute value of A, the larger the absolute value of the slope, the steeper is the line. So please remember that when we look at downward sloping lines, we are going to measure the steepness in terms of the absolute value of the slope. And the result will be opposite if we're looking at the mathematical values. Right. Now let us look at parallel and perpendicular lines as two special cases. So suppose we have two lines L1 and L2 with slopes M1 and M2 respectively. Then we have the first result, which is that two parallel lines have the same slope, which is to say that if our two lines L1 and L2 are parallel, then it must be true that M1, the slope of the first line, should be equal to M2. And this is a result which needs no proof, because if we have two parallel lines, if we have two lines that are parallel to each other, they have to have the same slope. Now, the second result is a result that needs some attention, needs a proof. Now, it says that if we have two lines which are perpendicular to each other, they have slopes that are negative reciprocals of each other, which is to say that if, let's say, line L1 is perpendicular to line L2, then M1 is going to be equal to minus 1 divided by M2. In other words, the product of the slopes, M1 times M2, is going to be minus 1. Let us see a visual representation of this. So here I have a line that passes through the points O and P, which is perpendicular to the line that passes through the points O and Q. Okay, so this angle in between the two lines is 90 degrees. Now you can see here that triangle OMP is similar to triangle QMO. And this is AA similarity. You can see that the angles are corresponding angles are same. So because of this AA similarity, we'll have that the ratio of the corresponding sides will be equal. So that we, if we look at the ratio of the sides opposite 90 minus alpha angle, so we'll have PM upon OM is equal to OM upon MQ. Okay, now PM upon OM is nothing but the slope of the first line, so that is M1, and OM upon MQ, let's look here. So the slope of the second line M2 is actually minus of MQ upon OM. The second line passing through the points O and Q is a negatively sloped line, so that the slope is given by minus of MQ, look at where my cursor is pointing, minus of MQ divided by OM, so that OM upon MQ is nothing but minus 1 upon M2, and that then establishes a result for the relationship between the slopes of two perpendicular lines. Now, we will quickly go through some formulas for a straight line. So we have established that the slope of a straight line that passes through 2 points x1, y1 and x2, y2 is given by A equal to y2 minus y1 divided by x2 minus x1. Now, suppose we have only one point, x1, y1, we have information on only this point, and let's suppose we have an equation which has, we have a straight line with slope A. Then we can write this slope A as y minus y1, just thinking of the other point x2, y2 as x, y. Therefore, the slope expression will become y minus y1 upon x minus x1. And now if we multiply both sides of this equation by x minus x1, we get the equation of a straight line, which is actually the point slope formula of a straight line, which is y minus y y1 is equal to the slope times x minus x1. And similarly, we can get at the point formula of a straight line, which is to say that if suppose you have information on 2 points on a straight line, then how would you write mathematically the formula for the straight line? So here in this case, we'll have, because we have information on 2 points, we can use this formula for the slope, which is y2 minus y1 divided by x2 minus x1. And because we have information on 2 points, we can use any one of these points to write our equation as y minus y1 is equal to y2 minus y1 divided by x2 minus x1 times x minus x1. So this is a situation where we don't know the slope, but we have information on 2 points, and we can plug that information in this expression here. Finally, in terms of the theory, let's look at the general equation of a straight line, which is ax plus by plus c is equal to 0. Here, please remember that both x and y have to appear in the first degree in this equation, and this equation holds for we'll just see that it does not hold for b equal to 0. So let's just talk about it. So this equation implies that y is equal to minus a upon b times x minus c upon b, and because this involves a division by 0 if b is 0, so we're going to impose the constraint that b is not equal to 0. Now you can see here clearly that this is the equation of a straight line with slope equal to minus a upon b and the intercept equal to minus c upon b. And with this, I finish my discussion of the theory for linear functions. In fact, before this discussion, Geetika and I had a short conversation about straight lines, and she had some queries. So let's hear her out.
Definitely, we would like to ask questions on the part of the students. But dear friends, if you wish to become part of this live session, then feel free to talk to us. Dear friends, you can become a part of this session by asking questions through our toll-free number. Our toll-free number is 1-800-110-430. I repeat, our number is 1-800-110-430. Friends, we are waiting for your calls. We have 15 minutes for this session. We are waiting, and till then I'll be asking questions from Dr. Niti Bhutani from your part, and we believe that your queries will be resolved. Ma'am, welcome once again, and as I already discussed with you that we are going to have a one-to-one session so that the students are benefited with the question answers round 2. Now the question is how the straight lines can be used by the economist for the policy purposes.
Right. Geetika, when I started this discussion, if you were listening to me, so there was this little bit that I said that, sometimes in economics, let me just roll back to that slide. Sometimes in economics, we have these non-linear relationships. Sometimes a graph can get complicated, or let's say, suppose you're trying to track the movement of a stock, stock prices or Sensex. So you might have really wacky graphs. And in that sense, a linear approximation to a non-linear relationship gives you a fairly good idea of what is happening. And let me walk you through this example that I had prepared, which actually sort of matches with your question and helps us answer your question. So this example comes from a United Nations report. Actually, it's based on an example from Sitsater and Hammond, the textbook that we use. But I've updated the figures from the latest report. So, that also gave me a sense of the population numbers, and I've changed the country. So the book had Europe as the example. I have taken the numbers for India because our audience is, I think, mainly Indian. So we have this United Nations report which gives us estimates for the population. And in 2000, in the year 2000, the population in India was estimated as 1053 million. And in 2010, the estimate was 1231 million. So the question is, can we construct some sort of a formula that we can use to make projections or see what the population might have been in some other year just on the basis of this information? So can we construct a linear function? And if I use these estimates to construct a linear function, basically I have here that the year 2000 corresponds to t equal to 0. And by the way, here my left-hand side variable is P, population, and the right-hand side variable X is T. So the year 2000 is T equal to 0, for which the population P is 1053. And for the year 2010, which would then become T equal to 10, the population is 1231. So if I can, what I can do here is, because I have 2 points, if you remember from your school, you can just join 2 points with a straight line. So because I have information on 2 points, I can use my point formula for the straight line. So my points are T1 comma P1 is equal to 0 comma 1053, and T2 comma P2 is equal to 10 comma 1231. So that then gives me my formula as P, because that's my Y variable. P minus 1053, I'm using this 0 comma 1053 as the point of reference. So that becomes P minus 1053 is equal to the slope, which is going to be 1231, P2 minus P1 minus 1053, divided by T2 minus T1, which is 10 minus 0. So that's a 10, and that has to be multiplied by T minus 0. So this in turn then gives us this equation, which is P is equal to 178 divided by 10 times T, plus I've taken the 1053 to the right hand side, and now I have an equation. So this is what I was talking about throughout. I have P is equal to 17.8 T plus 1053. Now we have an equation to represent population at a time T, and we want to know if we can use this equation for other times also. So basically we've started out with information on only 2 time periods, and the question is, can we use this equation to estimate the population in 2015? Or let's say 2020 or 2030. So can we make projections into the future? And this is the kind of stuff which people at IMF or World Bank, the base when you do basic work, this kind of stuff is done. So for example, if I want the population in 2015, then all I have to do is, in my equation, P equal to 17.8 times T plus 1053. All I have to do is put T equal to 15, because 2000 was T equal to 0. So 2015 becomes T equal to 15. And then I just, when I substitute T equal to 15, I get the population in 2015 as 17.8 times 15 plus 1053, which is 267. I hope I've got my calculations right. So 267 plus 1053. And this then turns out to be 1320 million, or 1.3 billion, which is actually very quite close to the UN estimate. So the report actually gave this estimate of 1309. And you can see here that from our calculation, we are getting 1320. So obviously the UN would be using other information also, and they would be using more sophisticated tools. This is something very elementary and raw. But yes, we are close to the population of today, which is 1.3 billion people. So I think that is quite exciting.
Disturb you over here because we have a caller right now.
Oh, great.
Hello.
Hello. Yes, ma'am. Good afternoon.
Yes, please tell your name and ask your question.
My name is Ajay Trivedi, and my question is that, suppose that, ma'am, there are 2 tables of that one.
Please repeat your question. Your sound is echoing.
My question is that, suppose we have 2 tables and...
Hello?
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 Yes, ma'am. Can you listen me?
Yes, actually your sound is echoing. I hope your television is slightly switched. The volume is... you have managed with the volumes of your television.
No, I just moved down right now. Hello?
Yes, dear friend, please ask a question.
Yes, my question is that, suppose we have 2 tables which are interrelated with that one.
We have 2 tables?
Yes, these are interrelated. Suppose in one table we have the population. Suppose that... And in the second table, and the relation with the population and education percentage. Suppose that 2,000 people are living in a city, and the percentage of their education is 750. Suppose that 750 are educated. So can we solve with these linear function with the linear function? We get the data about that one.
Friend, your sound is not properly reaching us, but as per your question, he is saying that if we have two tables, that is, and we want to calculate the population of the particular country, how to find out the entire thing. The question is little, hazy because we are not able to.
Well, that's exactly what I've been talking about because we just had 2 points in the table. We had information only on 2 time periods, and because we could fit a straight line, whenever we have information on 2 points, we can. If we've understood the question right, so we can fit a straight line and get the equation of a straight line that passes through these 2 points, and on the basis of that straight line, we can get rough estimates of what the population would be in other years because t is taking on different values. And so should I continue? Because
yes, we should continue.
We don't
dear friend, because your question we were not able to hear properly, but what you can do, you can write your question and send it to our email ID, and when next time Dr. Niti Bhutani will visit to us, we'll try to give your answer through the live session. So you can write your question through info.cec@nic.in. Thank you for calling us. Yes, ma'am.
Also, I think because his lectures are uploaded on YouTube, there's a comment section there, and you can always put your comment there and ask a question. Right, so this was to say that you could always make projections about what will happen in the future. Similarly, you could put t equal to, let's say, 19 and get an estimate of what you would get as a population in 2019. That's an estimate. But remember, again, these are raw tools, and we're not talking about more sophisticated stuff that the UN might be doing. Now, similarly, what we can do here is, as an extension, we can also go back in time, and suppose we want to estimate the population in 1970. So we could, in this case, put t equal to minus 30, and then if we do that, we get the population. I'm sorry, this is a typo, so this should have been 1970. So in this case, the population that we get for 1970 is 519 million, which is again not very off. It is off, but again, we are doing a very raw kind of calculation here with the straight lines. So the UN estimate is 553 million. So I still get the first digit right. Right, so this is how we use this kind of stuff. And also, I had this other example because you were talking in the beginning that people study demand and supply. So
yes, as discussed earlier, we were talking about that when students enter their colleges, and we have a curriculum in such a way that the students are required to study the demand supply analysis. Can the concept of straight line can be used?
Yes, that's absolutely right, because you can see here that I have an example where the demand function is given by A minus BP, which is nothing but a downward sloping line if we have B positive. By the way, here all our parameters A, B, alpha and beta are positive. The supply function is alpha plus beta P. So as we all know, the equilibrium price is such that it equates demand to supply. So if I call the equilibrium price P star, that would equate A minus B. P star would have to be equal to alpha plus beta times P star, which then gives us A minus alpha divided by B plus beta. And the corresponding equilibrium quantity is going to be A minus B times P star. So once I substitute the value of P star into my Q star, I'm going to get this expression, and that simplifies to A times beta plus B times alpha upon B plus beta. You can look at the algebra here because now we're running out of time. So I'll just quickly move to this little discussion which is kind of crucial, and actually after this I'll finish the topic. So let me just finish this. Now let us suppose there's an outward shift in the supply function. Now that is to say, let us suppose the new supply function is given by alpha bar plus beta P, and you can see here in the graph that the supply curve has shifted outwards. This is the kind of stuff that you do in micro, which is what Geetika was talking about. So now you can see in the picture that the equilibrium price goes down and the equilibrium quantity goes up, and we'll see that our math will also reflect the same. But before that, just note something which is very important. If you look at the intercept of the new supply curve, that is lower than the intercept of the old supply curve. So in that sense, one typically would think that this alpha bar is less than alpha. That is the kind of thing very often people tend to say. But remember here that In this case, actually, alpha bar is greater than alpha. And why is that? Because if you notice here, the way we've written the supply equation, we actually have quantity supplied on the left-hand side and price on the right-hand side. Whereas when we are drawing the graph, we have P on the vertical axis and Q on the horizontal axis. So please be careful with your axes, because that would, what you have on the left-hand side will then determine what your slope and intercepts would be. So if I suppose write this my supply curve as follows, with P on the left hand side, my original supply curve becomes P is equal to 1 by beta times S minus alpha by beta, whereas the new supply curve is P is equal to 1 by beta times S minus alpha bar by beta. Now, because our new intercept is lower than the old intercept, we have to have that this minus alpha bar by beta has to be less than minus alpha by beta, which is, and if I multiply both the sides of the inequality by minus 1, I get alpha bar is greater than alpha. So please make sure that you interpret your equations consistent with, you make your interpretation of your equations consistent with what you have on your graph, or what you have on the axes. And that's an important lesson for any economist, or when he or she is doing theoretical work. So anyway, the algebra students can manage on their own, the viewers can manage. So here the new equilibrium price we get is A minus alpha bar upon B plus beta, which is clearly going to be less than A minus alpha upon B plus beta, because we have that alpha bar is greater than alpha. So our new equilibrium price is less than the old equilibrium price, and similarly we get that the new equilibrium quantity is greater than the old equilibrium quantity. And I guess that's it from me. This is it.
With this note, we would like to thank you for giving your inputs to this particular lecture. Dear friends, we believe that you have gathered lots of information through this particular lecture. We believe that you might have questions, and if your questions are unanswered, feel free to talk to us through our email ID. You can post your questions as well as your feedbacks through info.cec@nic.in. Friends, this is the ID. You can put your questions there, and next time when Dr. Neeti Bhutani will visit us and we'll have another live lecture, there we'll try to give answers to your questions. Friends, this lecture is going to be uploaded on YouTube soon, so keep watching us, keep writing us, with the promise that we are taking your leave, that we are going to meet again soon. Thank you, ma'am.
Thank you so much. Have a great one, everyone.